Chapter 6 covers the electronic structure of atoms, but it's going to be a very big change of topics. But before we get into the details of the electronic structures of atoms, let me just address why we care in the first place. I want to provide a little bit of a historical background for why this is so fundamentally important for understanding chemistry. And this particular talk doesn't have any specific information that I'll be testing on. It's meant to give you a feel for why people care about this and why we're looking at these particular topics. So this sort of starts with the history of the invention of the Bunsen burner. Robert Bunsen in 1855 developed a burner to take advantage of brand new plumbing at the University of Heidelberg. Brand new stuff. Nobody had ever had a burner like this in their lab before. And the Bunsen burner has a control on it, this part down here, that allows you to change the amount of oxygen that you provide to the flame, and that allows you to control the temperature of the flame. And if you have this control closed, like it's shown here, you get a big yellow flame, which is much cooler than a blue flame. And as you open it up, you get progressively bluer and bluer flames. The hottest part of the flame is right at the tip of the blue part. And this is a very handy device that can produce very high temperatures. And once you have it, of course, you want to use it to do stuff. And what do you do with a burner? Well, you heat stuff. That's one thing you can do. So if you take a Bunsen burner and point it towards a nail, you've probably seen this effect before in a stovetop or something sticking in a fire. Things glow, we say, red hot or even white hot. And this is part of the English language now, based on observations of what things do when they get hot. If you get a nail head very hot, it glows and it gives off color. But the question is, why? Why does it give off these colors of light, and why these particular colors? And why, for example, is this top part where it's hottest glowing nearly white, but down here where it's cooler, it only glows red? What determines the colors that come off hot objects? That's an interesting question. We all have seen it. What makes it happen that way? Well, scientists tried to look at this in the 19th century to try to describe the colors given off by hot objects. And shortly before 1900, Lord Rayleigh and Sir James Jeans used classical physics to make a prediction. Now, don't worry too much about the details of this plot in terms of units or anything like that, but this axis is light intensity. So the higher on this axis, the brighter the light. This axis is something called the wavelength of light, which is a way of characterizing the color. So at 3000 Kelvin, you get this distribution of colors and intensities. And as you get to higher and higher temperatures, you get things that are in the visible range of light. So at 5000 Kelvin, you get this sort of distribution of colors of the rainbow being given off by a glowing object. But the equations that Rayleigh and Jeans worked out gave a line that looks like this. That's the classical theory developed by Rayleigh and Jeans, and it doesn't match the observed colors of light at all. In fact, so poor was this match that this fit was called the ultraviolet catastrophe. The catastrophe being that the equations didn't match observation at all. They double-checked, triple-checked their equations. All of the derivations were correct. It just didn't work. So this remains an outstanding puzzle, and we're going to address this in this chapter. Now, what else do you do if you've got a Bunsen burner and you haven't played with one before? Well, naturally, you try to burn stuff. And when you burn stuff, you quickly can find out that some substances change the color of the flame itself. In fact, this becomes the basis of what we call a flame test. We can use the color of a flame to identify elements present in the substance burning. This is a very useful analytical tool, and here's some examples of flame colors for different elements. Lithium makes a red flame, sodium more of a yellow flame, it looks kind of orangey here. Potassium, a light violet flame. Cesium, a violet flame, strontium, a bright red flame, copper, a distinctive green flame. And of course, once you get these different colors, different people came up with applications of this. One obvious application of different colors is fireworks, that's literally how fireworks work. The way you get different colors in fireworks is by knowing which colors are produced by which elements, and you can see some of these have been labeled by elements present to produce the color in the fireworks. But more fundamentally, why is it that copper produces a green flame? Why is it that strontium produces a red flame? Well, we need to look at the colors a little bit more closely. We use the word spectroscopy to refer to the study of the interaction of light and matter. We use spectroscopy in chemistry all the time. It's a very fundamental tool that we use. So we're going to look at the colors of energetically excited substances. To do that, first of all, instead of using a flame to excite the substance, we're going to put it in a high voltage. That's just a little bit more controlled way of generating light by exciting something. Then we're going to use a prism to spread the light out into all of the colors that it contains. So for example, if you take white light from the sun, for example, pass it through a prism, the prism will break it up into all of the colors of the rainbow. And in fact, this is literally how rainbows are formed. Light from the sun passes through little droplets of water in the air, rain, and it gets it's separated into all the colors of the rainbow, and that's why we get rainbows. So now if we apply this method to the light produced by excited elements, for example, suppose I take hydrogen. Here's a sample of hydrogen over here, and I put it in a high voltage so that it glows. It gives off the color of hydrogen. I pass that through a prism and break it up into its constituent colors. We only see 4 distinct colors. Well, actually 5. There's a very dim purple line there. When I have done this in a laboratory, I've never seen that 5th line, but technically it's within human visibility. So depending on how you count, you only get 4 or 5 bright lines. That's what these are referred to. This is a bright line emission spectrum. Which spectrum just means the set of colors given off by something. And there's only distinct lines. It's not all of the colors of the rainbow. And here's the puzzling part. It doesn't depend on how big the voltage is that we use to excite the hydrogen. We can double the voltage. The colors of light given off do not change. They are a characteristic of hydrogen itself. And in fact, each different element gives off its own set of bright line emission. In fact, we can use this as a fingerprint for elements. So for example, if this is the range of colors of the rainbow here, we see that sodium only gives off a handful of specific bright lines. Here's the lines for hydrogen again. Calcium has quite a few lines, but they're all very distinct bright lines. In fact, this is one way that we can tell what elements are present in distant stars. We take the light from the star, pass it through a prism, break it up into its bright lines, and identify which lines come from which element. It's a very powerful analytical tool, but still the question remains, why? What about hydrogen leads to those 4 bright lines? How can we possibly understand that? That's another of the goals of this chapter. Finally, material in this chapter is going to help us not only address those questions, but will lead to an understanding of the structure of the periodic table itself. That is, why do chemical properties revert periodically to being very similar? Why is it that the chemical properties of fluorine are very similar to those of chlorine? That oxygen is similar to sulfur and not oxygen similar to chlorine? Why those elements? We're going to understand that once we understand in detail the electronic structure of atoms, by which we mean where precisely are those atoms? We know that they're in some big fuzzy cloud outside of the nucleus, but we need more detail on describing where those electrons are. So as a start, hopefully this will help you understand why it is we want to understand spectroscopy, because that's the interaction of light and matter, and that leads to our understanding of the electronic structure. So to do that, we're going to start in the first section in chapter 6 by learning more principles about the nature of light itself, so that we can better understand its interaction with matter.